Recording in progress.
Perfect. Okay. So we're going to begin by talking about even and odd functions. Did Mr. Band talk about even and odd functions with you guys? Kind of. I taught algebra trigonometry for about a decade, so I never talked about it. Maybe did. It's a pretty simple topic. It seems a little funny at first, but a function is even if this happens. And a function is odd if this happens. It might seem a little cryptic at first. Just bear with me. I'm going to clear things up in a moment. But if f of negative x equals f of x, that's called an even function. If f of negative x equals negative f of x, that's called an odd function. Graphically, what that means is that the function is symmetric about the y-axis. Examples, y equals x squared. That's a great example. And let me copy and paste. That's why I love Zoom. Here the function is symmetric about the origin. For example, y equals x cubed. I'll give you other examples too. Y equals sine x. Much better. Here y equals cosine x. Just to give you other ones that are not necessarily polynomials. Okay, so let's think about it. If I graph y equals x squared, the graph looks like this, right? Hey, Sebastian. Thanks, appreciate it. Oh, yeah. Actually, I'll just take it here. I'll click these for fun. All right. So y equals x squared. Think about it. Symmetry, right? This is the left side, so it goes to the right side. So, for example, if I plug in, say, 2.5, I know it's not a weird number, but if I plug in 2.5, you get 6.25, right? What if I plug in negative 2.5? Do I still get the same output? Yeah, the output does not change. So that's really what's happening. If the output does not change, if I simply change the sign of the input, it's an even function. So actually, let me state that because I kind of like what I just said. So sorry, it's a little conceited. But if the output does not change when the sign of the input changes, then the function is even. Okay, there's absolutely no change. Oh, that's terrible. It's in the way of other stuff. Here we go. If the output does not change when the sign of the input changes, the function is considered even. That guarantees a symmetry about the y-axis. That's called an even function. That's what this means, right? See how these outputs are the same, even though the signs of the input change? Okay, so I think I beat that one to death. Now for odd functions, another thing really quickly I want to say too. Cosine x. You guys should know cosine x looks like this, right? That's also symmetric about the y-axis. Also think about it too, like identities, right? What would do cosine of pi over 6? So quick quiz in the unit circle. What's cosine of pi over 6? That's it?
1/2.
Yeah. No. That's pi over 3. You just signed root 3 over 2, good. Now what's cosine of negative pi over 6? Still the same thing. It's still getting, and the reason why is because if you think about the unit circle, right? Pi over 6 is right here. Negative pi over 6 right here. Cosine correlates to the x coordinate on the unit circle, right? So the x coordinate does not change sign on the first and fourth quadrants, right? So even if you're going this way or that way, counterclockwise or clockwise, the cosine is going to maintain the same value regardless of which direction you're moving in, as long as you're going the same magnitude in either direction. So again, those are even functions. Sometimes people like to think, oh, the exponent's even, like x squared, but again, it applies to non-polynomial functions too, right? So it's really more about the outputs staying the same. Now, odd functions. X cubed looks like this, right? or sine x looks like this. Now, that's where you have to kind of visualize this really well. Think it's like a little spinner or a pivot point. What if I were to spin this graph 180 degrees? Or spin the sine graph 180 degrees? That's what it means to think about the origin. If you do a 180-degree rotation, so this means, Ethan, do you have a slip? Okay. If you do a 180-degree rotation and get back to the same place, that's an odd function. So what this means, hold on a sec. If the output merely changes sign when the input changes sign, then the function is odd. Okay, so that's what's happening with that. So, but if it's totally different, like if the output, like say you change the sign of the input, let's say originally the output was like 2, now it's like 4, or -5, now it's 10 or whatever, that's neither. That's gonna be a really weird one. Like if you do a transformation to this, like you move it left to right or whatever, you do some weird stuff, then forget about it. It's not going to be either of those two things. So that's what's happening. Okay, so hopefully that explanation helped. Now let's actually prove it. When you prove it, you can prove it graphically. You can prove it algebraically. Or you can prove it numerically. There are 3 ways you could prove. Now, I'm going to emphasize this because you guys can handle that. I think for more remedial class, I'd probably do it numerically. So let's do numerically first. So see how that looks. And when you do numerically, you can be hypothetical. Choose any number you want. Choose an easy number. What number do you want to plug in that's easy to plug in? Let's do 1. Let's do 1. Actually, no, let's do 2. The reason why I don't want to do 1 because the output's gonna be 0. Yeah, let's not do 1 because the output's gonna be 0. Let's pick a number so the output's not 0. So what's the output if I plug in 2? -12. Yeah, -12. Perfect. Good. Great. Okay, now let's switch the sign of the input. What's the output now? -12. Still same, right? Because why? Because you're raising each variable to an even exponent. Of course, it's going to stay the same. It should. Okay. Let's look at it graphically. I'm not going to try to imagine that in my head. So let's actually go to Desmos. Y equals x squared minus x to the 4 power minus. There you go. Does that look symmetric to you? About the y-axis? Yeah, 100%. I totally got totally have that y-axis symmetry, right? So that looks good to me. I like it. Right? All's good there. Okay, algebraically. This is what I really care about. Here's what you gotta do. You literally have to replace x with negative x. It's like a composite function. That's why we cover this after composite functions. So you literally replace x with negative x. What happens if you square negative x? What does it become? Square or raise negative x to the 4 power. Yeah, doesn't change, stays the same. So when you do that comparison, you simply compare it to that. Or if all the signs change, if it went from negative x squared to positive x4, then it would have been odd in that case. But Yeah, so those are the three ways of doing it. And this is what I was talking about. Like, we want to be able to see things numerically, see things graphically, see things algebraically. It doesn't get any more concrete. These three modes of learning the math, it doesn't get any more concrete than this, right? Numerically, plug in a number, see what happens. Does it satisfy the concept? Yeah, it does. Graphically, see what happens. Satisfy the concept? Yeah, it does. Algebraically, do it. Do the algebra. Does it satisfy the concept of even function? Yeah, it does. Every single time, we're confirming it. Now we got more confidence, right? Because now I've proven it's three different ways. It's even, right? There's no ifs, ands, buts about it. All right. Go and try B. Doing the same exact thing. Yeah, plug in two. Don't plug in one, because you can get zero as your output. Plug in two, see what happens. Graph it, see what happens. Replace x negative x, see what happens. Tell me when you're done. So early in the morning, just mental math. 32, 34. Do you guys get 18 as the output? Mm-hmm. Yeah, both times you get, and then they only get negative 18, right? Cool. And then graphically, again, not going to attempt to do that one. X to the fifth minus 2x cubed plus x. Yeah, if you were to rotate that 180 degrees, I totally get back to the same configuration, right? So let the origin be the pivot point, like a spinner, like in one of those like war games you play, right? We get back to the same place. And then lastly, what I really care about is the algebraic. And I'll make sure I'll specify that. Anytime you raise a negative term to an odd power, the sign will change. Or the output is just negative. But if you have an extra negative, it becomes positive. So is g of negative x the same thing as negative 1 times g of x? You bet, right? Because if I put a negative in front of this function, what happens to all the terms here? You multiply by negative 1, they all change sign. Negative x flat plus 2x cubed minus x. Boom. There we go. So that's going to be an odd function. Some people or some textbooks or some online resources will show it like this. It's the same thing. Personally, I like to do this because I like to see if I make this input change, what's my output change? My output change means what was originally is negated, or all the signs change sign. Sorry, all the terms change sign. All right, so cool. Next one's kind of interesting. I know that one's going to be odd. How do you think I know that? Without really showing any math on the screen. Good, yeah.
Like,
Go out, yeah.
plug in negative x, so you know that there's like x to the third, for example, and you know that's going to get influenced by the negative. It's
Yeah.
multiplied 3 times.
The top won't get influenced at all.
Yeah.
But the top will stay as is. But the bottom will change. And what happens when you have a fraction or a rational function? You know, if you change just one portion of it or one part, like the denominator change sign, then overall it goes to negative, right? So we are going to see that. So if I were to, I'm just going to do this algebraically. Can't do threes on this. I don't know why. So top stays as is, but a bottom changes sign for sure. So is that the same thing as saying negative h of x? It is, because if you do negative 1, if you do negative 1 times this, I guess, you know, the negative 1 could go to the top or the bottom. It's up to you. If I put it to the bottom, because think about what negative 1 really means. It can mean a couple things. It could be negative 1 over 1 or 1 over negative 1, right? So yeah. And so these are the same. So it's an odd function. H negative x does equal negative h of x. And if you graphed it, you'd see the same thing. So, all right, cool. So that's even odd functions. Hopefully you guys feel good about that. We can move on to inverses. Inverses, I know you guys have seen. Not to worry about that. Very simple. You switch x and y, and you solve for y. That's all you're ever doing. So the domain range of one relation will be reversed. So the inverse relation of the inverse relation of relation A has a domain that has the range of relation A. Wait, sorry. Has a domain that is the range. Oh, sorry, that's right. The inverse sounds very confusing. Let me just clear this up. Well, let me read this. What's going on here? This is like so confusing. A relation is not a function. Let me just draw pictures here. That might help you guys. All right. So for example, this will fail the vertical line test, right? And that relationship is x equals y squared. But what would its inverse be?
Y equals x.
Y equals x squared, which would be a function now. So in that case, that would pass the vertical line test. Or relation is you know what? I think it's just this is terribly confusing. I don't like this. Let's just cross this off. I don't like it. Let's keep it simple for you guys. Let's keep it really, really simple here. This is what I want you guys to say. Swap x and y and solve for y. Find the inverse. Also, the domain range for original function gets swapped for inverse. And lastly, okay. That's really what I want to say. I just think that's confusing. So you guys should know swap x and y, solve for y. That's plain inverse, right? That's the most basic way we deal with this, right? The domain range for the original, they get swapped, as they should, because that's y squared, right? Good. And lastly, if the original function passes the horizontal line test. Now, if obviously I should say the original relationship, I should change that term, but I'll just call it function. Let's assume that your f of x passes the vertical line test, so itself is a function, cool. If it also passes the horizontal line test, then the inverse itself will be a function, meaning that the graph of the inverse will pass the vertical test. Let me give you guys some. I know I'm not doing this on the screen, but let's take a look at y cosine x. Okay, does that pass the vertical line test? Yes, that's the function, right? That's the function. Does it pass the horizontal line test? No. Now what's the inverse? So first of all, x equals sine y, and if you get y by itself, you get this, right? Did Mr. Brand show you the graph of these? Did not do that?
No.
Okay, it's not really bad. But did he tell you that there's only one there's a default range? You guys learn about that maybe? Yes, here's the thing. If you actually were to graph it, the graph would kind of look like this. It'd be kind of weird, but just trying to think here. If you try graphing, it would look like this. It's kind of like a snake. But see, you run into a problem, right? That totally failed the vertical line test. So what you would have to do is when you graph it, and we'll talk about this when we get the trig in their next unit, I think. And remember, y is now going to be angles, and that's going to be opposite of hypotenuse. We know that what's the max here for sine? A -1. So that's 1 and -1. But in order to constrict this, we go from pi/2 to -pi/2. That's why inverse sine has to have a default range. We'll talk more about this when we get to the next unit in a couple weeks. That's why this has to have a default range, because you need to guarantee it's a function. Does this pass the vertical line test now? It does, because you force the issue by constricting this between -pi/2 and pi/2. We'll talk more about that later on, because inverses are a big deal in trig. So don't worry if you don't quite get it yet. I'll clear it up when we get there in 2 weeks. But as I said, horizontal line test we have to consider to see if the original function's inverse is a function also. So functions inverse is also function is called 1-to-1, meaning every x is paired with unique y, and vice versa, every y is paired with unique x. So what are examples of not 1-to-1? That's not 1-to-1. Because it fails the horizontal line test. Whereas something like this here, y equals x cubed, it passes both vertical and horizontal line tests. Because think about it, what's the inverse? Or cube root of x, which looks just like this. Right? So, very simple. And again, domain range will just swap. So if f is 1-to-1 function domain D in range R, the inverse function is denoted by this with a -1 symbol. If the function with domain R in range D defined by, I'm not sure what's supposed to be meant by that last blank. Hold on. I'm not sure. Let's just ignore that. Sorry, guys. I'm not sure what's going on with that. We'll just move on. All right. Yeah, sorry about that, guys. But anyway, here's what I do know. It's symmetric. The graphs of f and inverse of f are symmetric about y equals x. So y equals x goes right to the middle of both those graphs. So if you were to cut out a piece of, like, let's say actually you literally did this in your notes. You take some scissors, you cut out a square piece, and you fold that square piece along the dotted line. Will both graphs map onto each other? They will. Yes, so that's what's meant by the symmetry. They will. As they should, because you literally are swapping the x and y values. I think I know what this means right here. I think we, and that probably was what's probably meant on the earlier page. That is a true statement I'm writing right now. If you plug the inverse into the original, or plug the original into the inverse, if the output is always x, you guys may have learned that before also. You guys might remember when you have something like this here, if f of g of x equals x, and g of f of x. When this phenomenon happens, f and g are inverses of each other. I think that's what's supposed to be on those blanks in the previous page, but that's okay. I'm going to explain it here. But you might remember that from last year. If you have two functions and the composites always result in x, or they happen to equal each other, because of course they equal x, then they're inverse of each other. And same thing over here. I mean, it's just, I'm using the inverse notation, but composite rule, right? There we go. So yeah, in many cases, you have a function is inverse is not a function. That's totally fine. When that happens, we'll have to restrict the domain, as you see down here with y equals x squared and x equals y squared. So we'll talk about it in just a moment. Any questions on this so far? No? All right, let's keep moving. So, for example, y equals x squared. What if I just restrict this domain? Right? That's y equals x squared with the caveat that x is greater than or equal to 0. So y equals root x is like that. Because technically speaking, it's x equals y squared. And we solve for y. Where are you supposed to put when you solve for y? Where are you supposed to put? Yeah, plus or minus. But you guys see why it's a problem to put plus or minus. Because now you have two outputs, right, for one input. So in order to guarantee that this passes the vertical line test for the inverse, you just keep the positive. So that's why you kind of need that that restriction. So that way the inverse is also going to be a function. So you have to do that. Otherwise, then you're going to have something like this here, right? And that's a problem. All right, let's keep moving. All right, so let's look at this graph here, which should be really easy. I know you guys know how to do this. What's the transformation here, by the way, for root x plus 3 compared to root x? Go 3 left, exactly right. And if I plug in 1, I get 2. So what's my domain for this guy? Yeah, -3 to infinity was interval notation. And the range will be 0 to infinity, right? Okay, now let's go red for the inverse. So clearly just going to swap the x and y values, right? Or x equals root y plus 3. Then you get x squared equals y plus 3. Or y equals x squared minus 3. That's algebraic what's happening. But you're not truly going to graph that, right? Because think about it. If your domain range for the original is this, what's the domain range for the inverse? Switch, right. So your domain is going to be restricted from 0 to infinity. Has to be. And the range is also going to be restricted. So at 0, I get -3. Plus you swap the x and y values, right? Like, let me go back to blue again. Let's look at this numerically also. So we're going to do all 3 modes: numerical, algebraic, graphical, right? So you don't have to make a table. I just felt like making one. Should have probably done that earlier. It's all right. So guess what? The inverse switches, right? They all switch. 0, -3, 1, -2, 2, 1, right? Hope that makes sense. And is it symmetric about y equals x? You bet. Totally symmetric about y equals x, 100%. And does that domain range make sense? 100% it does too. So that's how you do it accurately. So this is kind of the big takeaway for today. Make sure we know our inverses really well. I mean, of course, we talked about even odd functions, but yeah, this is a big takeaway. Questions? No? All right. All right. Why don't you guys try example 10? I'll do as well, and then we'll move on to transformations after that. I'll do it too. Cloud method just means just graph it. Just do your transformations. Don't worry so much about that. Hopefully you know your vertex at 4, 1. All right, here we go. So clear that's parabola, vertex 4, 1. Here to your symmetry, right? So 5, 2, 3, 2. Those are the 2 other points you can plot. Not 1 to 1, don't horizontal line test. Therefore, the inverse of fx won't be a function. If you want to restrict the domain, so the force issue, that the inverse will be a function, then I'll just do the right side for force infinity, 1 to infinity. Don't have a left side to that problem. Just have a right side to it. If you want, you can have a left side to it too, I suppose, but it's better to keep things positive. I don't know. And then to find the inverse, switch x and y, solve for y, which I did. And that's going to be a radical function with that domain range, which is simply the reverse of the domain range of part C. So that's a good question too. Probably a very good test question, actually. I like that question a lot because it kind of encapsulates a lot of things we've been talking about so far, right? So questions? We're good? Say go ahead, yeah.
Can you ask us to stay the domain range? You want us to stay to the restricted?
Well, I'll be clear about that. Yeah. I'll say, you know, what would you have to do to make sure that the inverse will also be a function, right? Which it does say right there. So there you go. Okay. Probably graph that. Just I know some people still copy stuff down. You don't have to copy the graph, but probably graph the inverse 1, 4. But obviously I'd have to restrict that. Yeah, and see how it's right. So it makes sense, right? What I just did. All right, now let's talk about transformations. So you guys should be pretty comfortable with transformations. So we'll just kind of just get into it. Let's go on example 11. Consider a function y with the factor f of 3. Well, of course I know 2 points, 3, 5, and a, b. Duh. Of course I know that. Okay, so then how does it transform? Okay, I see what they're getting at. I got it. Okay. That's up 4. That's right 4. Here you're gonna multiply y by 2. Careful this one. What's gonna happen with 3x on the inside? You guys know? You divide x by 3 to counteract it. So up 4 means you add 4 to y. Right 4 means you're going to add 4 to x. So in this case, you have 3, 9, or a, b plus 4. Here you're going to have 7, 5, or a plus 4, b. Here you're going to have 3, 10. Or here you're going to have 1, 5, or essentially a, 2b, or a over 3, b. So it should be pretty. Does that make sense? You guys did the stuff right. Yeah, right. Yeah, so yeah, that's all there's to it. We're gonna still talk more about transformations on Thursday. The homework, I don't think we'll have transformations, but there'll be the 4th homework assignment is all in transformations. So we're gonna revisit this in 3 days or our next 2 class meetings. Okay, and then lastly, and this is where I kind of want to end things. So 3 common negative 5, a common negative b. So you multiply y by negative 1. Here you multiply x by negative 1. And this also is going to be reflection. About what axis, guys, when you put a negative out in front? If it's a vertical flip, what are we flipping over? X-axis. I know it's kind of weird to call it a vertical flip, but because x is a horizontal coordinate. But yeah, that's what happens. And that's a reflection the other way. And don't say flip, guys. You guys are better than that now. We're not in middle school. Reflect about, we want to be more formal. We want to say reflection. Reflect about y-axis. So it goes this way, right? When you put a negative inside, it goes this way. So that's going to be negative 3 comma 5. Negative a comma b. Okay. Cool. Yeah. All right. Well, now we got a lot of stuff going on. PEMDAS. I cannot emphasize that anymore. You got to use PEMDAS to deal with this stuff. What's the first thing I see, sir? So you better take care of that. So you gotta go 3 left. So that's going to be 0, comma. So you're going to go 3 left. Okay, after you do that, what's the next thing you see? Right, because you multiply for your add. M comes for A and PEMDAS. So you're gonna multiply y by 2. And the third step is going to be add 1 to y. So that becomes 11, right? Because I had to multiply y by 2 and then add 1. So take 3 away from x. We get 2b plus 1. Okay. So 3 left means he takes 3 away from x, right? All right, here. 2x minus 1. What's the first thing x sees now? It's a 2. So you got to divide x by 2. Then you're going to add 1 to x. And then 3 down, which is vertical, right? So it'll be 7 comma 2. Or in this case, oh my goodness. What a mistake I make, guys. Yeah, I got to divide by 2. I multiplied by 2. Yikes. So 2.5. My apologies. Or I'll just say 5 halves. My apologies, guys. Or, and I caught myself when I did the next one, right? I caught myself there. Sometimes it's good to do algebraically first. Yeah, a over 2 plus 1, then b minus 3. That's what happens there. Okay, so just we'll revisit this on Thursday, as I said. And just to wrap things up, for example, 11, what did you notice about the transformation of the point A, comma B in part B? Well, I don't know. Just follow the same thing as 3, comma 5. Not sure what's meant by that question. Let's not worry about that question. This question seems lame to me. I didn't make these notes, by the way. I just borrowed them from the previous teachers. So anyway, it's all good. Homework is this. You guys about 10 minutes. I know it's not the 25-minute classes where you have like 25 minutes work on homework. So you can get a head start if you want, or if you're just a little tired, just need to, don't get your phones out. Go to the bathroom if you need to. But want to get a head start on homework, you may. So this right here, it says homework number 2 on top. It gives you the question numbers. I'll put it in Schoology as well as an assignment. Even odd stuff, which we talked about. 12 does talk about inverses, which is good. 28 through, okay, piecewise functions, just deal with it. I didn't talk about it. Yeah, more even odd stuff. A word problem looks like we got that one. Domain. And then 36, 39, 43, 48. Yeah, composites. Yeah, there we go. I think we're good. All right. Let's cut off. We were on the board, guys. Sorry about that. Hold on. Let me just display it. I'll stop the recording. Here we go.
Yeah, you do.
There you go.
Well, no, you do it, yeah. So X.